Imagine a black hole so massive that its event horizon alone could swallow our entire solar system. Not once, but many times over. A black hole that outweighs the one sitting at the center of our own Milky Way by a factor of roughly 25,000. Most supermassive black holes are already almost impossible to comprehend, millions of times the mass of our Sun. But this one exists on an entirely different level. Estimated at around 100 billion solar masses, Phoenix A doesn't just sit at the extreme end of the scale, it practically defines the extreme end. It lives inside one of the most violent galaxy clusters ever discovered, feeding on torrents of superheated gas at rates that challenge what astrophysicists thought was even possible. Tonight, we're going to understand what Phoenix A truly is, how it became this enormous, and why it earned the title of cosmic monster. Before we go any further, if you enjoy these deep explorations of the universe, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a massive difference for me. Now, let's begin. Let's start with what we know. Because before we can understand what makes Phoenix A so extreme, we need a frame of reference. We need to know what a supermassive black hole normally looks like, how massive they typically are, and how far their boundaries typically stretch. Without that baseline, the numbers for Phoenix A won't land the way they should. They'll just sound like bigger versions of already big numbers. And you'll miss what makes this object genuinely different from almost everything else in the known universe. At the center of our galaxy, the Milky Way, roughly 26,000 light years from where you are right now, sits a supermassive black hole called Sagittarius A star. Its mass is approximately 4 million times the mass of our Sun. 4 million suns. Every one of those suns is a thermonuclear furnace over 800,000 miles across, fusing millions of tons of hydrogen every second, radiating enough energy to warm planets and sustain entire ecosystems from millions of miles away. And Sagittarius A star contains the mass of 4 million of them, compressed into a single object so gravitationally intense that not even light itself can escape once it crosses the boundary. That boundary, the event horizon, has a radius of roughly 12 million kilometers. To give that some perspective, our Sun has a radius of about 696,000 kilometers. The event horizon of Sagittarius A star extends about 17 times farther from its center than the surface of the Sun extends from the Sun's core. If you placed it at the center of our solar system, it would fit comfortably inside Mercury's orbit. It's a genuinely large object by any human measure. But in the context of the solar system, it's relatively contained. You can point to it on a diagram. You can say it sits here between the Sun and Mercury, and the rest of the solar system stretches out beyond it, largely unaffected at planetary distances. We know Sagittarius A star is there because we've watched its gravitational effects in extraordinary detail. Individual stars near the galactic center orbit this black hole at tremendous speeds. One star, known as S2, completes a full orbit every 16 years, reaching velocities of roughly 2.5% of the speed of light at its closest approach, about 7,600 kilometers per second. A star, being flung around a single object at that speed. The precision of those orbital measurements is what allowed astronomers to pin down Sagittarius A star's mass with remarkable confidence. It's one of the best measured supermassive black holes we know of. And at 4 million solar masses, Sagittarius A star is actually on the modest side for a supermassive black hole. Most large galaxies harbor one at their center, and the mass range is enormous. Some supermassive black holes weigh in at a few million solar masses, like ours. Others climb into the billions. The black hole at the center of M87, the giant elliptical galaxy in the Virgo cluster, has a mass of about 6.5 billion solar masses. That's more than 1,000 times the mass of Sagittarius A star. In 2019, the Event Horizon Telescope collaboration produced the first ever direct image of a black hole shadow. And it was M87's black hole they captured. 6.5 billion solar masses, with an event horizon large enough to swallow our entire solar system out past Pluto with room to spare. At the time, it was celebrated as one of the most massive black holes known. There are others in a similar weight class. TON 618, a distant and brilliantly luminous quasar, hosts a black hole estimated at about 66 billion solar masses, though that figure carries notable uncertainty. Holm 15A, a galaxy at the center of the Abell 85 cluster, harbors a black hole estimated at roughly 40 billion solar masses. These are the heavyweights, the upper end of the scale. Objects so massive that astrophysicists sometimes use the word ultramassive to distinguish them from the more common supermassive black holes, sitting in the millions or low billions. These are the context. These are the objects that have traditionally represented the most extreme examples of black hole growth in the observable universe. Billions of solar masses compressed behind event horizons, stretching across light hours of space. Enormous by any definition. And then there is Phoenix A. Phoenix A sits at the center of the Phoenix cluster, one of the most massive galaxy clusters ever discovered, roughly 5.8 billion light-years from Earth. Astronomers studying the cluster's central galaxy used established scaling relations to estimate the mass of its central black hole. The result was staggering. Depending on the method and the assumptions used, the mass came in at approximately 100 billion times the mass of our Sun. 100 billion. Not million, not single-digit billions. 100 billion solar masses. A black hole that, if the estimate holds, outweighs TON 618 by roughly 50%. A black hole that dwarfs M87's already enormous 6.5 billion solar mass black hole by a factor of more than 15. A black hole that contains roughly 25,000 times more mass than Sagittarius A star, the gravitational anchor of our entire galaxy. Now, I need to be upfront about something important here. That 100 billion solar mass figure is an estimate, and it carries significant uncertainty. Measuring the mass of a black hole nearly 6 billion light-years away is not like stepping on a scale. Astronomers cannot observe Phoenix A directly. They infer its mass from indirect evidence, from the way stars move in the surrounding galaxy, from the relationship between a black hole's mass and certain measurable properties of its host galaxy, from scaling relations calibrated on nearer, better understood systems. These methods work well in the middle of the range, but at the extreme end, the uncertainties grow substantially. The true mass of Phoenix A could sit at 70 or 80 billion solar masses, or it could be close to the published figure, or even somewhat higher. What the data tell us with reasonable confidence is that Phoenix A is among the most massive black holes ever identified, very likely in the range of many tens of billions of solar masses. and potentially reaching 100 billion. That's the honest picture. An extraordinary mass, but one we should hold with appropriate scientific humility about the specific number. That said, even the conservative end of those estimates is astonishing. Let's work with the general ballpark and explore what a mass in this range means in physical terms. Because even at 70 or 80 billion solar masses, the picture we're about to paint barely changes. The ratio between Phoenix A and Sagittarius A star is staggering. At 100 billion solar masses versus 4 million, Phoenix A is roughly 25,000 times more massive. Let me put that in perspective with something tangible. Our Sun is about 330,000 times more massive than Earth. That's the difference between a planet and a star. The difference between a rocky world with oceans and an atmosphere and a thermonuclear ball of plasma that dominates an entire planetary system. The mass ratio between Phoenix A and Sagittarius A star is a meaningful fraction of that planetary to stellar gap. The difference between our galaxy's supermassive black hole and Phoenix A is proportionally in the same territory as the difference between a rocky planet and the star it orbits. Except, both of these objects are already black holes. Both are already operating at scales far beyond anything in ordinary human experience. And yet one of them dwarfs the other the way a star dwarfs a planet. Imagine a cosmic balance. On one side, you place Sagittarius A star, 4 million solar masses, the gravitational anchor of the Milky Way. On the other side, you begin stacking copies. 2 Sagittarius A stars, 10, 100, 1,000. You keep stacking. 5,000 copies of the supermassive black hole at the center of our galaxy. Still not balanced. 10,000, 15,000, 20,000. Still not balanced. You need roughly 25,000 copies of Sagittarius A star, 25,000 complete replicas of the black hole anchoring a galaxy of hundreds of billions of stars, just to equal the estimated mass of Phoenix A. Or consider it from the Sun's perspective. Our Sun contains roughly 99.86% of all the mass in the solar system. Everything else, Jupiter, Saturn, all the rocky planets, every moon, every asteroid, every comet, every grain of dust drifting through the Kuiper Belt, all of it combined is a tiny sliver of the Sun's mass. The Sun is dominant. It is the overwhelming gravitational presence for everything within light years. Now, imagine 100 billion of those suns. Every star in the Milky Way, if they were all roughly the mass of our Sun, would total somewhere around 200 to 300 billion solar masses. Phoenix A, a single black hole, contains a mass roughly equivalent to a third or even half the total stellar mass of our entire galaxy. One object, rivaling the combined mass of hundreds of billions of stars. But mass, as overwhelming as these numbers are, is only part of the picture. What does an object with this much mass actually look like in physical space? How much room does it take up? This is where things become genuinely difficult to hold in your mind. The event horizon of a black hole scales directly with its mass. If you double the mass, you double the radius of the event horizon. This means Phoenix A's event horizon is roughly 25,000 times larger than the event horizon of Sagittarius A star. Sagittarius A star's event horizon has a radius of about 12 million kilometers. Phoenix A's event horizon has a radius of approximately 2,000 astronomical units. Let me build that up piece by piece so you can feel it. 1 astronomical unit is the average distance from Earth to the Sun. It's about 150 million kilometers, or roughly 93 million miles. Light, traveling at 300,000 kilometers per second, the fastest speed anything in the universe can achieve, needs 8 minutes and 20 seconds to cover 1 astronomical unit. That's the distance from the surface of the sun to the ground beneath your feet. 1 astronomical unit. Mercury orbits at about 0.4 astronomical units from the sun, Venus at 0.7, Earth, by definition, at 1, Mars at 1.5. These are the rocky inner planets, the small warm worlds closest to our star. All 4 of them fit within a sphere roughly 1.5 astronomical units in radius. That's the inner solar system, the region where we live, the neighborhood we know best. Then come the gas and ice giants. Jupiter orbits at about 5.2 astronomical units, Saturn at 9.5, Uranus at just over 19. Neptune, the outermost major planet, orbits at roughly 30 astronomical units from the sun. 30 astronomical units. It takes light about 4 hours to travel from the sun to Neptune. 4 hours at 300,000 kilometers per second, and it still needs that long to cover the distance. That's how far away Neptune is. Beyond Neptune lies the Kuiper Belt, home to Pluto, other dwarf planets, and countless icy bodies left over from the solar system's formation. The outer edge of the Kuiper Belt sits at roughly 50 astronomical units from the sun. Beyond that, our solar system extends into the vast, mostly empty space, stretching eventually toward the distant Oort cloud, thousands of astronomical units out. But in terms of the major structures we've explored with spacecraft, the solar system as we know it occupies a sphere roughly 50 astronomical units in radius. The event horizon of Phoenix A has a radius of 2,000 astronomical units. 2,000 astronomical units. That is 40 times the distance from the sun to the outer edge of the Kuiper Belt. It is roughly 67 times the orbital radius of Neptune. If you placed Phoenix A at the center of our solar system, where the sun sits right now, the event horizon would extend outward through every single planetary orbit. Past Mercury, past Venus, past Earth, past Mars, past the asteroid belt, past Jupiter, past Saturn, past Uranus, past Neptune, past Pluto, past the entire Kuiper Belt, and then it would keep going. It would keep extending outward, past Voyager 1, past Voyager 2, deeper into interstellar space than any human-made object has ever reached. And it would still keep going, stretching to a boundary roughly 40 times beyond the Kuiper Belt's edge. Everything inside that sphere, our entire known solar system, all of it, would be swallowed whole, lost deep inside the event horizon, with the boundary stretching dozens of times farther in every direction. Consider what it means to be inside an event horizon. Nothing returns. No light, no radio signal, no particle of any kind can travel outward past that boundary. Inside the event horizon, the curvature of space-time is so extreme that all paths, even paths taken by light itself, lead inward toward the center. If our solar system were placed inside Phoenix A's event horizon, we would not see the stars. We would not see other galaxies. We would not detect the cosmic microwave background or the glow of the Big Bang. Every photon, every gravitational wave, every piece of information from the universe outside would be completely and permanently cut off. Every probe we had ever launched, every telescope we had ever built, every signal we had ever sent would be trapped inside with us. We would exist in a one-way universe, falling inward with no possibility of escape and no possibility of communication with anything beyond the horizon. That is the nature of an event horizon. It is not a surface you can touch or see. It is a boundary woven into space-time itself, beyond which causality flows in only one direction, inward. Now think about the light crossing time, because this is perhaps the most visceral way to feel how enormous Phoenix A truly is. Light travels at 300,000 kilometers per second. Nothing is faster. It can circle Earth about 7.5 times in a single second. It covers the distance from Earth to the Moon in about 1.3 seconds. It crosses the full diameter of Sagittarius A star's event horizon in roughly 80 seconds. About 1 minute and 20 seconds. That might sound fast, but remember, light circles Earth 7.5 times in a single second. Even at that speed, it needs over 1 minute to cross the black hole anchoring our entire galaxy. Light needs approximately 11 days to travel from the edge of Phoenix A's event horizon to its center. 11 days. And to cross the full diameter from one edge of the event horizon to the opposite edge, light would need roughly 23 days, more than 3 weeks. The fastest thing in the universe, traveling at its absolute maximum speed, which nothing can surpass, needs more than 3 weeks to cross a single black hole. For comparison, light needs about 4 hours to travel from the Sun to Neptune. That same light would need 23 days to cross Phoenix A. The ratio is extraordinary. Light crosses our solar system's breadth in hours. It crosses Phoenix A in weeks. A single black hole, measured in the time it takes light to traverse it, is over 100 times larger than the distance between the Sun and the most distant major planet. Here's another way to feel this scale. Voyager 1, launched in 1977, is the most distant human-made object from Earth. It has been flying through space for nearly 50 years, traveling at about 17 kilometers per second. That's roughly 61,000 kilometers per hour, about 400 times faster than a car on a highway. After all those decades of relentless travel, Voyager 1 is approximately 164 astronomical units from the Sun. It has crossed the boundary where the solar wind gives way to interstellar space, farther from home than anything humans have ever built, and it's still barely 8% of the way to the edge of Phoenix A's event horizon. After nearly 50 years of continuous, uninterrupted flight through the vacuum of space, Voyager has covered less than 1/10 of the distance to the boundary of a single black hole. If Voyager 1 had been launched from the center of Phoenix A at its current speed, it would need over 550 years to reach the event horizon. 5.5 centuries. That takes you back to before Columbus crossed the Atlantic, before the Protestant Reformation reshaped Europe, before Copernicus proposed that Earth orbits the Sun. The founding of every modern nation, the scientific revolution, the industrial revolution, the invention of powered flight, the space age itself, all of it fits within the time Voyager would need to cross the radius of a single black hole. Over 5 centuries of continuous flight at 61,000 kilometers per hour, and you're still only traveling from the center to the edge. This is what we are dealing with. Not just a number printed in a journal, not just 100 billion solar masses written on a page. A real, physical region of warped space-time so vast that it makes our entire solar system look like a mote of dust inside a cathedral. The event horizon alone is a void stretching thousands of astronomical units in every direction, requiring weeks for light to cross, and centuries for our fastest spacecraft to traverse. The mass inside that boundary is equivalent to a substantial fraction of every star in the Milky Way combined. Most people, when they picture a supermassive black hole, are imagining something roughly on the scale of Sagittarius A star, a few million solar masses. An event horizon you could fit inside a planetary orbit. Something enormous by any human standard, but still something you can anchor to a diagram of the solar system and point to. You can say it's about this big. You can compare it to the sun. You can place it next to a planetary orbit, and the comparison holds. Phoenix A shatters those reference frames. You cannot place it on a diagram of the solar system because it swallows the diagram. You cannot compare its event horizon to a planetary orbit because it contains every planetary orbit with vast room to spare. The analogies that work for ordinary supermassive black holes don't just strain under Phoenix A's weight, they collapse entirely. The mental toolkit we use to visualize cosmic objects, scaling things against the Earth or the Sun or the distance to Neptune, that toolkit is not built for something of this magnitude. We need entirely new comparisons, and even those can only approximate the reality. So how does an object like this come to exist at all? How does anything in the universe accumulate 100 billion solar masses behind a single event horizon? This is not a trivial question. There are physical limits on how fast a black hole can grow. There are forces that actively push back against the inflow of matter, creating feedback loops that should slow or even halt the growth long before it reaches this scale. Most supermassive black holes in the universe grew to a few million or a few billion solar masses and then plateaued. They reached a kind of equilibrium, massive enough to dominate their host galaxies, but constrained by their own energy output and the dwindling supply of fuel. They stopped growing. They settled. Phoenix A didn't settle, or if it did, it settled at a level that was already almost beyond comprehension. Somehow, over the roughly 13.8 billion year age of the universe, this black hole found conditions that allowed it to keep growing, keep feeding, keep accumulating mass at rates that push against the theoretical limits of what should be possible, not through any exotic or unknown mechanism, but through a combination of circumstances so extreme that they appear to exist in very few places in the observable universe. The right environment, the right host galaxy, the right supply of infalling matter, the right conditions sustained not for millions, but for billions of years. Understanding those conditions requires looking at the place where Phoenix A lives. Not just the galaxy it anchors, but the vast structure surrounding it. The Phoenix cluster is one of the most extraordinary objects in the sky. A galaxy cluster so massive, so luminous in X-rays, and so actively evolving that it creates the perfect conditions for building a monster. Everything about the Phoenix cluster sits at or near the extreme end of what has ever been observed. Its total mass, its X-ray brightness, the rate at which gas cools and flows inward toward its center, the rate at which new stars are being born in its central galaxy. All of it is extraordinary, and all of it connects directly to the growth and the staggering scale of Phoenix A. But before we go there, hold onto the picture we've built. A black hole whose event horizon could swallow our entire solar system dozens of times over. An object so massive that it rivals the total stellar mass of entire galaxies. A gravitational well so deep that light itself needs more than 3 weeks to cross it. Among the handful of ultramassive black holes known to exist in the observable universe, Phoenix A sits at or near the very top of the scale, though the exact figure remains uncertain and may shift as future observations sharpen the measurement. This single object outweighs the black hole at the center of our own galaxy by a factor of roughly 25,000. It outweighs the famous black hole in M87, the first ever directly imaged, by more than 15 times. This is not merely a big black hole. This is a black hole pressing against the boundary of what the universe appears capable of producing. There are theoretical arguments suggesting that black holes cannot easily grow much beyond this range within the age of the cosmos. The time constraints, the feedback mechanisms, the finite supply of matter available, all of it conspires to impose a ceiling. And Phoenix A appears to be pushing against that ceiling. It is not just extreme, it is close to the maximum, an object that represents the very outer edge of what billions of years of relentless accretion, galactic mergers, and cosmic engineering can build. That raises a question that will carry us through the rest of this journey. If there is a ceiling on black hole growth, if there are forces and limits that constrain how massive these objects can become, how did Phoenix A reach a mass where it's pressing against that ceiling? What combination of environment, history, and physics created the conditions for this particular black hole to grow so large while almost every other one in the universe stopped far short? The answer lies in the Phoenix cluster itself, in the torrent of superheated gas filling the space between its galaxies, in the cooling flows that funnel matter inward toward the cluster's heart at rates unmatched in almost any other known cluster, in the extraordinary star formation blazing through the central galaxy, hundreds of solar masses of new stars forming every year, a birth rate so extreme it's been called a starburst, at a scale rarely seen at the center of any galaxy cluster. And in the delicate balance, or rather the profound imbalance, between the energy Phoenix A pumps back into its surroundings and the relentless inflow of matter that refuses to be fully stopped, this black hole didn't grow in isolation. It grew because the universe built a machine around it. A vast, intricate, violent machine of gas and gravity and energy, operating across billions of years, channeling matter from across an entire galaxy cluster toward a single point. Phoenix A is the product of that machine, and the machine, the Phoenix cluster, is one of the most extraordinary structures we've ever found. That is where our journey takes us next, into the heart of the cluster, into the furnace that built the monster. To understand how Phoenix A became what it is, you can't just look at the black hole, you have to look at where it lives, because a black hole doesn't grow in a vacuum. It grows because something feeds it, and the thing feeding Phoenix A is one of the most extraordinary structures in the observable universe. Galaxy clusters are the largest gravitationally bound objects that exist, not the largest structures in the universe. Those would be the filaments and walls of the cosmic web, threads of matter stretching hundreds of millions of light years across. But those structures aren't gravitationally bound. They're not held together by their own gravity into a single coherent object. They're just patterns in the distribution of matter, shaped by gravity but not imprisoned by it. Galaxy clusters are different. They are genuine objects. Collections of hundreds or even thousands of galaxies, all locked together by mutual gravitational attraction into a single enormous system. They orbit within a shared gravitational well, bound to each other the way planets are bound to a star, though on an incomparably larger scale. A typical massive galaxy cluster might contain anywhere from a few hundred to several thousand individual galaxies. But here's what surprises most people. The galaxies themselves, the bright, visible collections of stars that give clusters their name, are actually a minor component of the total mass. If you added up every star in every galaxy in a large cluster, you'd account for only about 2 to 3% of the cluster's total mass. Stars are a rounding error. There's a second component that outweighs the galaxies by a factor of roughly 5 or 6. Between the galaxies, filling the vast spaces that separate them, sits an ocean of gas. Not cold gas like you'd find in a molecular cloud where stars are born. Not the thin, wispy gas drifting through interstellar space within a galaxy. This is something far more extreme. It's called the intracluster medium, and it's one of the most hostile environments in the known universe. The intracluster medium is superheated plasma, gas that has been heated to such extraordinary temperatures that atoms can't hold onto their electrons. Hydrogen, helium, and heavier elements are all fully ionized, stripped down to bare nuclei swimming in a sea of free electrons. The temperatures in the intracluster medium of a massive cluster typically range from tens of millions to over 100 million degrees. For context, the core of our sun, where nuclear fusion occurs, where hydrogen atoms are being crushed together under millions of atmospheres of pressure to form helium and release the energy that powers all life on Earth. That core reaches temperatures of about 15 million degrees. The gas floating between galaxies in a massive cluster is routinely hotter than the center of a star. In some clusters, substantially hotter. This superheated gas radiates energy. At these extreme temperatures, the primary form of radiation is X-rays. The electrons in the plasma are moving so fast, carrying so much thermal energy, that when they interact with ions, they emit high-energy photons, X-ray photons that stream outward in every direction. A massive galaxy cluster glows in X-rays like a cosmic lantern. You can't see it with your eyes. Human vision detects only a narrow slice of the electromagnetic spectrum, the wavelengths we call visible light. But point an X-ray telescope at a galaxy cluster, and it lights up. The intracluster medium blazes with X-ray emission, filling the space between galaxies with a diffuse, intensely hot glow that can be detected from billions of light years away. The third, and by far the largest component of a galaxy cluster, is something we can't see at all: dark matter. Roughly 80 to 85% of a cluster's total mass is dark matter. A substance that doesn't emit light, doesn't absorb light, doesn't interact with ordinary matter through any force except gravity. We know it's there because of its gravitational effects. The galaxies in a cluster move too fast. If you add up all the visible matter, all the stars and all the gas, there isn't nearly enough gravity to hold the cluster together. The galaxies should fly apart. They don't. Something invisible is providing the extra gravitational pull. That something is dark matter, and it dominates the mass budget of every galaxy cluster in the universe. So a galaxy cluster is, in order of mass, about 85% dark matter, about 12 to 13% hot gas in the intracluster medium, and about 2 to 3% stars and galaxies. The galaxies, the bright objects we actually photograph with our telescopes, are floating like luminous specks in a vast invisible ocean of dark matter and superheated plasma. This is the type of structure that surrounds Phoenix A, but the Phoenix cluster is not a typical galaxy cluster. In almost every measurable property, it sits at or near the extreme end of what has been observed. The Phoenix cluster was identified around 2010 by the South Pole Telescope, a 10-meter microwave telescope sitting at the geographic South Pole in Antarctica. The South Pole is one of the best places on Earth for this kind of observation, because the atmosphere above it is extraordinarily dry and cold, which minimizes interference with the faint microwave signals the telescope is designed to detect. The telescope found the Phoenix cluster not by looking for galaxies or X-rays, but by looking for a specific distortion in the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky. When photons from the cosmic microwave background pass through the hot gas of a galaxy cluster, some of those photons collide with the high-energy electrons in the intracluster medium. The electrons kick the photons to higher energies, distorting the smooth spectrum of the background radiation. This is called the Sunyaev-Zeldovich effect, and it creates a distinctive shadow in microwave observations, a telltale signature that a massive galaxy cluster is sitting along the line of sight. The stronger the signal, the more massive and hotter the cluster. The Phoenix cluster produced one of the strongest signals the South Pole telescope had ever detected. Right from the start, it was clear this was something exceptional. Follow-up observations confirmed what the initial detection suggested. The Phoenix cluster sits roughly 5.7 to 5.8 billion light-years from Earth, deep in the southern constellation of Phoenix, which gives the cluster its name. Its total mass, including dark matter, is estimated at roughly 2.5 quadrillion solar masses. To write that as a number, you'd write a 2 and a 5 followed by 14 zeros. It's one of the most massive galaxy clusters known, not the single most massive. There are a handful of comparably heavy clusters scattered across the observable universe, but the Phoenix cluster sits comfortably in the top tier, a true heavyweight among structures that are already the largest gravitationally bound objects in existence. But what makes the Phoenix cluster truly extraordinary, what sets it apart from other massive clusters and connects it directly to the extreme growth of Phoenix A, is not just its total mass, it's what happens to the gas at its center. Because the intracluster medium in the Phoenix cluster isn't just sitting there, glowing passively in X-rays, it's doing something dramatic. The gas in the intracluster medium loses energy as it radiates X-rays. Every X-ray photon that streams away from the cluster carries energy with it. Energy that was part of the thermal motion of the gas. As the gas loses energy, it cools, and as it cools, it becomes denser, because cooler gas at a given pressure occupies less volume. This denser, cooler gas sinks toward the center of the cluster, pulled by the gravitational well of the dark matter and the central galaxy. As it sinks, it gets compressed further by the weight of the gas above it, and it radiates more X-rays, losing more energy, cooling further, sinking further. It's a self-reinforcing cycle, a river of gas flowing inward from the outer regions of the cluster toward the very center, driven by the relentless loss of energy through radiation. Astrophysicists call this a cooling flow. In clusters where this process is especially prominent, the central region is called a cool core. The gas in the cool core is still incredibly hot by everyday standards, tens of millions of degrees, but it's measurably cooler than the gas farther out. The temperature drops as you move toward the center because the gas there has been radiating and cooling for longer. Many massive galaxy clusters have cool cores and some degree of cooling flow. It's a common phenomenon, but the Phoenix cluster's cooling flow is in a class of its own. X-ray observations from the Chandra X-ray Observatory, one of the most powerful X-ray telescopes ever built, revealed that the rate at which gas cools in the Phoenix cluster's core is staggering. Classical estimates, based purely on the X-ray luminosity and gas density, suggest that gas could be cooling and flowing inward at a rate equivalent to thousands of solar masses per year. The actual rate at which gas fully cools to low temperatures and drops out of the hot phase is debated, and almost certainly lower than the classical estimate, because various heating processes partially offset the cooling. But even the more conservative spectroscopic estimates suggest that the effective cooling rate in the Phoenix cluster is among the highest ever measured in any galaxy cluster. Hundreds of solar masses of gas per year may be cooling and flowing inward toward the center of this system. Hundreds of solar masses per year. Think about what that means. Every year, a mass equivalent to hundreds of stars like our Sun cools out of the intracluster medium and flows inward. Not once, not in a special burst. Continuously, year after year, century after century, potentially for hundreds of millions of years or longer. The gas streams inward from the vast reservoir of the intracluster medium, pulled by gravity, cooled by radiation, funneling toward the one place everything in the cluster is ultimately directed toward, the center. And what sits at the center? At the very heart of the Phoenix cluster, at the bottom of its gravitational well, sits the brightest cluster galaxy. Every massive galaxy cluster has one. It's the largest, most luminous galaxy in the cluster, typically a giant elliptical galaxy that grew to its enormous size by consuming smaller galaxies over billions of years. As the cluster assembled, as galaxies fell in from surrounding space and merged with the growing structure, the central galaxy acted as a gravitational sink. Smaller galaxies spiraling inward through dynamical friction gradually lost orbital energy and merged with it. Over cosmic time, the brightest cluster galaxy absorbed dozens or even hundreds of smaller systems, growing larger and more massive with each merger. Their stars were added to its own. Their gas was stripped away and incorporated. Their central black holes, in some cases, may have merged with the black hole already sitting at the center. The brightest cluster galaxy in the Phoenix cluster is enormous. Even by the standards of brightest cluster galaxies, which are already among the most massive galaxies in the universe, this one stands out. It sits at the exact center of the cluster's gravitational well. Embedded in the densest, most luminous part of the X-ray emitting gas, surrounded by hundreds of other galaxies that orbit within the cluster's gravitational embrace. And it's not just sitting there passively. This galaxy is doing something that most brightest cluster galaxies are not doing. It's forming stars at a ferocious rate. In most massive galaxy clusters, the brightest cluster galaxy is relatively quiet. It's old. Its stars are mostly ancient, reddish, low-mass stars that formed billions of years ago. Star formation has largely shut down. The gas that might have fueled new starbirth has been either consumed, expelled, or kept too hot to collapse. The central galaxies in most clusters are red and dead, as astronomers sometimes colloquially describe them. Not literally dead, of course. They still contain hundreds of billions of stars shining steadily. But they're not making new ones. Not in any significant quantity. The Phoenix cluster's central galaxy is the dramatic exception. Observations across multiple wavelengths, from ultraviolet to infrared, reveal that new stars are forming in this galaxy at a rate of roughly 500 to 800 solar masses per year. Some estimates push even higher. To appreciate how extraordinary this is, consider that the Milky Way forms new stars at a rate of roughly 1 to 3 solar masses per year. 1 to 3. The Phoenix Cluster's central galaxy is forming stars hundreds of times faster than our entire galaxy. It's not a gentle glow of steady star formation. It's a blaze, a starburst rivaling the most extreme star-forming galaxies observed anywhere in the universe, except this one is happening at the center of a galaxy cluster, a location where such extreme activity was long thought to be impossible. Where is all that star-forming gas coming from? The cooling flow. The connection is direct. The superheated gas in the intracluster medium radiates X-rays, cools, and flows inward. When it reaches the central galaxy, it cools further, potentially reaching temperatures low enough for the gas to condense into molecular clouds. The dense, cold clumps of gas from which stars form. The Phoenix Cluster's extraordinary cooling flow is delivering enormous quantities of gas to the central galaxy, and that gas is collapsing to form stars at a rate almost unmatched in any other known cluster. And this is where Phoenix A enters the picture. Because the gas doesn't just form stars, some of it continues inward, past the stellar orbits, past the inner regions of the galaxy, deeper and deeper into the gravitational well, until it reaches the innermost region of all, the accretion zone around the central supermassive black hole. Phoenix A sits at the absolute center of this system. It is the final destination of the inflow, the last stop at the bottom of one of the deepest gravitational wells in the known universe. Everything that flows inward, everything that the cooling flow delivers, everything that isn't intercepted by star formation or blown outward by feedback, all of it converges on this one object. Picture the geometry, a galaxy cluster spanning millions of light years across, one of the most massive gravitationally bound structures in existence. Within it, an ocean of plasma at tens of millions of degrees, radiating X-rays with extraordinary luminosity. That gas, losing energy through radiation, cooling and flowing inward at hundreds of solar masses per year, converging on a central galaxy that has grown enormous through billions of years of galactic mergers. And at the precise center of that galaxy, the focal point of the entire colossal structure, a single black hole. This is not an accident. The extreme mass of Phoenix A is not a random outlier. It's the natural product of an environment that was essentially designed by physics and gravity to funnel mass toward a single point. The Phoenix Cluster is a machine, a cosmic engine of accretion, and Phoenix A sits at the very center of that engine, receiving the output of a process that has been operating for a significant fraction of the age of the universe. Compare this to a more typical situation. Consider the Milky Way. Our galaxy is large and respectable, containing a few 100 billion stars, but it's relatively isolated. It sits in the local group, a small collection of a few dozen galaxies gravitationally bound together with only two large members, the Milky Way and Andromeda. There is no intracluster medium blazing in X-rays. There is no cooling flow funneling thousands of solar masses of gas toward the center. The gas supply reaching Sagittarius A star is modest, a trickle, not a torrent. Our black hole has been on a starvation diet for most of the Milky Way's history. It occasionally captures a wayward gas cloud or unlucky star, flares briefly, and then settles back into quiescence. It grew to 4 million solar masses and essentially stopped. Not because it couldn't grow larger in principle, but because there simply isn't enough fuel reaching it at a fast enough rate. The environment doesn't support it. Now, consider M87, a far more massive galaxy sitting at the center of the Virgo cluster. M87 is a giant elliptical galaxy with about 1 trillion stars and a 6.5 billion solar mass black hole at its center. The Virgo cluster is a substantial galaxy cluster with over 1,000 member galaxies and a significant intracluster medium. There is a cooling flow, though it's relatively modest by the standards of the most extreme clusters. M87's black hole grew much larger than Sagittarius A star because it had access to far more fuel, both from the gas in its own massive galaxy and from the intracluster medium of the Virgo cluster. It reached billions of solar masses, but even M87's environment pales in comparison to the Phoenix cluster. The cooling rate is lower, the gas supply is less extreme. The result is a black hole that, while enormous, is still more than an order of magnitude less massive than Phoenix A. The pattern is clear. Larger clusters with more intense cooling flows produce more massive central galaxies with more massive central black holes, and the Phoenix cluster, sitting at the extreme end of cluster mass and cooling rate, produced one of the most massive black holes ever observed. The environment scales with the outcome. Phoenix A didn't reach 100 billion solar masses by defying physics. It reached that mass because it lives in one of the most extreme environments physics can create. But there's a complication, a puzzle that astrophysicists have been wrestling with for decades, and one that the Phoenix cluster illuminates in a particularly dramatic way. In theory, cooling flows should be even more extreme than what we observe. The classical calculations, based purely on how fast the gas radiates X-rays and loses energy, predict cooling rates far higher than what we actually measure when we look for the cooled gas. In many clusters, the classical prediction suggests thousands of solar masses per year should be cooling, but we only find evidence for tens or hundreds. Something is partially stopping the gas from cooling. Something is heating the gas, partially counteracting the radiative losses, keeping the intracluster medium hotter than it would otherwise be. That something is the black hole itself. This is the feedback problem, and it's one of the most important concepts in modern astrophysics. When gas falls toward a supermassive black hole, it doesn't just quietly disappear. Before it crosses the event horizon, the gas swirls into an accretion disk, a spinning disk of matter spiraling inward like water circling a drain. As the gas spirals, it heats up through friction and compression, reaching millions or even billions of degrees. And along the poles of the accretion disk, some of that energy gets channeled outward in the form of jets. Relativistic jets. Columns of matter and energy launched at speeds approaching the speed of light, drilling outward from the black hole's poles into the surrounding gas. These jets carry staggering amounts of energy. When they plow into the intracluster medium, they inflate enormous cavities, bubbles of relativistic plasma that push the hot gas aside and pump energy into their surroundings. These cavities are visible in X-ray images as dark voids in the otherwise bright intracluster medium. They can be tens of thousands or even hundreds of thousands of light years across. The energy they inject into the gas heats it, partially offsetting the radiative cooling, slowing the cooling flow, and reducing the amount of gas that ultimately reaches the central galaxy and the central black hole. In most cool core clusters, this feedback roughly balances the cooling. The black hole feeds on infalling gas, launches jets, the jets heat the gas cools more slowly, less gas reaches the black hole, the jets weaken, the gas starts cooling faster again, more gas reaches the black hole, and the jets strengthen once more. It's a thermostat. A self-regulating cycle that keeps the system in approximate equilibrium. The black hole never fully starves, but it also never gorges itself. It grows slowly, modestly, constrained by its own energy output. The Phoenix cluster appears to be a system where this thermostat is overwhelmed. Phoenix A does produce jets. It does inflate cavities in the surrounding gas. Observations have confirmed the presence of large cavities in the X-ray emission, clear evidence that the black hole is actively pushing back against the cooling flow. But the cooling flow is so powerful, so relentless, so energetically dominant that the jets can't fully counteract it. The gas keeps cooling. The inflow continues. Stars keep forming at hundreds of solar masses per year. And the black hole keeps being fed at rates that are extraordinary by any standard. This is what makes the Phoenix cluster so scientifically valuable. It's not just another galaxy cluster with a big black hole. It's a system that appears to be caught in a transitional state, a state where the balance between cooling and heating is tipping in favor of cooling. We're seeing a system where the feedback mechanism that normally constrains black hole growth is losing the battle. The cooling flow is winning, and the consequences are visible everywhere. In the extreme star formation, in the massive gas inflows, and in the staggering mass of Phoenix A itself, a black hole that grew to tens of billions of solar masses or more because the environment around it kept delivering fuel faster than the black hole's own energy output could shut off the supply. This raises a deeper question. If the cooling flow is currently overwhelming the feedback, how long has this been going on? Is this a temporary state, a brief window in the cluster's history where conditions aligned to produce extreme inflow? Or has the balance been tipped for hundreds of millions of years, giving Phoenix A a sustained period of extraordinary growth? The answer matters enormously for understanding how the black hole reached its current mass. A brief episode of enhanced feeding, lasting only a few tens of millions of years, wouldn't add much to a black hole that already weighs tens of billions of solar masses. But a sustained imbalance, lasting hundreds of millions or even billions of years, could have contributed substantially to its growth over cosmic time. We don't know the answer with certainty. The Phoenix cluster gives us a snapshot, a single moment in the life of a system that has been evolving for billions of years. We see it as it was 5.7 billion years ago, because that's how long the light has taken to reach us. What happened before that moment and what has happened since are questions we can only approach through theoretical models and simulations. But the models suggest something striking. The conditions in the Phoenix cluster, its extreme mass, its powerful cooling flow, its enormous central galaxy, these are not features that developed overnight. They are the product of billions of years of hierarchical assembly, of galaxy clusters merging with other clusters, of gas accumulating and heating, of the gravitational well deepening and the cooling flow intensifying. Phoenix A didn't grow to its current mass in a single feeding frenzy. It grew because the Phoenix cluster has been building the conditions for extreme growth over most of the age of the universe. The machine has been running for a very long time. And the machine, as extraordinary as it is, operates on principles that are not exotic or mysterious. Gravity pulls matter together. Gas radiates energy and cools. Cooled gas flows inward. Some of it forms stars. Some of it feeds the black hole. The black hole pushes back with jets. In most clusters, the jets win and the system regulates itself. In the Phoenix cluster, the cooling flow is so powerful that the jets fall short. The details are complex, but the underlying physics is straightforward. Gravity, thermodynamics, radiation, and feedback. These are the forces that built Phoenix A. Not some unknown process, not some violation of physical law, just the known laws of nature, operating at their most extreme in one of the most extraordinary environments the universe has ever produced. That environment, the Phoenix cluster, is the reason Phoenix A exists at the mass it does. Without the cluster, without the intracluster medium, without the cooling flow, without the billions of years of gas delivery, there is no path to 100 billion solar masses. The black hole and the cluster are not separate stories. They are two parts of a single story. A story about what happens when the universe builds the most massive gravitationally bound structure it can, fills it with superheated gas, and lets gravity do its work for billions of years. But Phoenix A did not grow through accretion alone. The cooling flow is a critical piece of the puzzle, but it's not the entire puzzle. There is a second channel of growth, one that operates on a completely different timescale and through a completely different mechanism. When galaxies collide, when their central black holes are drawn together by gravity and friction and ultimately merge, the resulting black hole inherits the combined mass of both. In a cluster environment like the Phoenix cluster, where the central galaxy has been growing for billions of years by absorbing smaller galaxies, these mergers may have contributed substantially to Phoenix A's mass. Accretion feeds the black hole continuously, but gradually. Mergers feed it in sudden, dramatic leaps. Together, these two processes, operating in the most extreme environment available, built the black hole we see today. Understanding how these two growth channels work, how they interact, and why they were able to push Phoenix A to the extreme end of the mass scale requires a closer look at the physics of black hole growth itself, at the limits that should have stopped it, and at the reasons those limits appear to have been exceeded. Black holes don't just appear at 100 billion solar masses. They start small, and they grow. Everything about a black hole's final size depends on how much matter it can consume, how fast it can consume it, and how long the feeding continues. These sound like simple questions, but each one conceals layers of physics that constrain and complicate the growth process in ways that make an object like Phoenix A genuinely difficult to explain. The fact that it exists at the mass it does tells us something important. Not just about this one black hole, but about the limits of what the universe can build when conditions align. So let's start at the beginning. Not the beginning of Phoenix A specifically, because we don't have a detailed birth certificate for any individual supermassive black hole, but the beginning of the process. How do supermassive black holes get started? And what determines how large they ultimately become? Every supermassive black hole started as something much smaller. This seems obvious, but the details matter enormously. The initial object, the seed from which a supermassive black hole eventually grows, sets the starting point. And the starting point affects everything that follows. If you start with a larger seed, you need less time and less fuel to reach a given final mass. If you start with a smaller seed, you need more of both. There are two main theories for how these seeds form. The first is the stellar remnant pathway. In the very early universe, the first generation of stars formed from pristine hydrogen and helium gas. The only elements that existed before stars began manufacturing heavier elements through nuclear fusion. These first stars, sometimes called population 3 stars, are thought to have been extraordinarily massive, perhaps hundreds of times the mass of our Sun. When these massive stars exhausted their fuel and died, they collapsed, and some of them would have formed black holes. These stellar mass black holes would have been relatively small by supermassive standards, perhaps a few tens to a few hundred solar masses, small seeds, far from the billions or tens of billions of solar masses we see in the largest supermassive black holes today. But they were a starting point. The second pathway is direct collapse. In certain rare conditions in the early universe, massive clouds of primordial gas may have collapsed directly into black holes without ever forming stars first. If a gas cloud was large enough, dense enough, and critically if it lacked the ability to cool efficiently, it could collapse under its own gravity into a single object with a mass of perhaps 10,000 to 100,000 solar masses. These are called direct collapse black holes, and they represent much larger seeds. Starting from 100,000 solar masses rather than 100 solar masses gives you a significant head start. You're closer to the finish line before you even begin accreting. We don't know which pathway produced most supermassive black holes. It's possible both pathways operated, with different seeds forming in different environments. Some supermassive black holes might trace their ancestry to a single massive star that died in the first few 100 million years after the Big Bang. Others might have formed from direct collapse events in especially gas-rich regions of the early universe. The answer might also vary from one black hole to another. Phoenix A's seed could have been either type or something in between. What matters for our story is what happened after the seed formed. Because regardless of whether Phoenix A started at 100 solar masses or 100,000, it had to grow by a factor of at least 1,000,000 to reach its current estimated mass. That growth had to happen within the roughly 13.8 billion year age of the universe, and that growth was governed by rules. The most important rule governing black hole growth is the Eddington limit. This is a fundamental physical constraint, not a technological limitation or an engineering problem. It's a consequence of the basic interplay between gravity and radiation, and it sets a speed limit on how fast a black hole can swallow matter under normal circumstances. Here's how it works. When gas falls toward a black hole, it doesn't fall straight in like a rock dropping into a well. The gas has angular momentum, which causes it to spiral inward, forming a rotating disk of material called an accretion disk. As the gas spirals closer to the black hole, it gets compressed and heated by friction between adjacent layers of the disk, moving at different speeds. The inner regions of the disk, closest to the event horizon, reach staggering temperatures, millions or even billions of degrees. At these temperatures, the gas radiates an enormous amount of energy, primarily as X-rays and ultraviolet light. This radiation streams outward in all directions, and radiation carries momentum. When a photon strikes a particle of gas, it pushes that particle outward, away from the black hole. The more radiation the accretion disk produces, the stronger this outward push becomes. At some point, the outward radiation pressure exactly balances the inward pull of gravity. This balance point is the Eddington limit. If you try to feed the black hole faster than the Eddington rate, the radiation produced by the infalling matter becomes so intense that it blows the incoming gas away. The black hole's own luminosity creates a wind that pushes its food supply back out into space. It's like trying to pour water into a drain that's blowing air upward so hard the water can't get in. The Eddington limit depends on the black hole's mass. A more massive black hole has stronger gravity, which means it can hold onto gas against a stronger radiation field. So more massive black holes have higher Eddington limits. They can eat faster in absolute terms. But there's a catch. The timescale for growth is set by the ratio of mass gained to mass already present. And that ratio is roughly constant regardless of mass when accreting at the Eddington limit. This means that the time it takes to double a black hole's mass by accreting at the Eddington rate is roughly the same whether the black hole is 100 solar masses or a billion. That doubling time, called the Salpeter time or the E-folding time, is approximately 40 to 50 million years, depending on how efficiently the accretion disk converts matter into radiation. 40 to 50 million years per doubling. That sounds fast enough, right? The universe is 13.8 billion years old. 45 million years goes into that hundreds of times. Surely that's enough doublings to grow from any reasonable seed to 100 billion solar masses. Let's count. Starting from 100 solar mass seed and doubling every 45 million years at the maximum possible rate, how many doublings does it take to reach 100 billion solar masses? 100 billion is 100 followed by 9 zeros. 100 is 10 squared. 100 billion is 10 to the 11th power. The ratio is 10 to the 9th, or about 1 billion. To grow by a factor of a billion through doublings, you need about 30 doublings. Since 2 to the 30th power is approximately 1 billion, 30 doublings at 45 million years each gives about 1.35 billion years. That's within the age of the universe. It seems feasible. But this calculation assumes the black hole accretes continuously at the Eddington limit for over a billion years without interruption. Every single moment. For over a billion years, it must be fed at the maximum possible rate. No gaps, no pauses, no periods where the gas supply dwindles or the black hole runs out of fuel. That's an extraordinarily demanding requirement, and it's almost certainly unrealistic for most black holes in most environments. In practice, black hole accretion is episodic. Gas doesn't flow steadily inward like water through a pipe. It arrives in bursts, triggered by events like galaxy mergers that funnel fresh gas toward the center, or by perturbations in the galactic gas supply. Between these active episodes, the black hole can sit quietly for hundreds of millions of years, consuming very little. Most supermassive black holes spend the majority of cosmic time in a relatively dormant state, accreting far below their Eddington limit. Sagittarius A star is a perfect example. Right now, it's essentially starving. The accretion rate onto Sagittarius A star is estimated at a tiny fraction of the Eddington rate, perhaps a millionth or less. It occasionally flares when a small gas cloud drifts too close, but these events are brief and infrequent. For most of the Milky Way's history, its central black hole has been on a severe diet. This is why it stopped at 4 million solar masses. Not because 4 million is some hard limit, but because the gas supply ran out. The Milky Way's central region simply doesn't deliver enough fuel to sustain significant growth. Even the Eddington limit itself may be somewhat flexible. Under certain conditions, black holes may be able to temporarily exceed the Eddington rate. This is called super Eddington accretion, and it's thought to occur when the geometry of the inflow is different from the standard thin disk model. If gas falls in from all directions simultaneously, forming a thick, puffy structure rather than a thin disk, the radiation can be trapped within the inflow and carried inward with the gas, rather than escaping outward to push against incoming material. The radiation gets swallowed along with the matter, reducing the outward pressure and allowing gas to fall in faster than the Eddington rate would normally permit. Super Eddington accretion is particularly important in the early universe, when the first supermassive black hole seeds needed to grow very quickly to explain the massive quasars we observe at high redshifts. We see quasars powered by billion solar mass black holes existing less than 1 billion years after the Big Bang. Growing a billion solar mass black hole in under 1 billion years is very difficult with standard Eddington limited accretion, especially if the seed was small. Super Eddington episodes in the early universe may have been critical for getting the first supermassive black holes off the ground, but Super Eddington accretion can't be sustained indefinitely. It requires specific conditions, particularly a very high rate of gas delivery to the black hole's immediate vicinity, and those conditions don't last forever. Eventually, the gas supply diminishes, or the black hole's own energy output disrupts the inflow, and accretion drops back to sub-Eddington rates, or ceases entirely. This brings us to the second major growth channel, mergers. When two galaxies collide and merge, their central black holes can eventually find each other and coalesce into a single, more massive black hole. This process contributes mass without requiring accretion. The two black holes simply combine, and the resulting black hole has roughly the sum of their masses, minus a small fraction radiated away as gravitational waves during the merger. Galaxy mergers are common in the history of the universe. The hierarchical model of structure formation tells us that galaxies grow by merging. Small galaxies merge to form larger ones, large galaxies merge to form even larger ones, and galaxy clusters form from the merger of galaxy groups. This process has been ongoing since the first galaxies formed and continues today, though at a slower rate than in the early universe. Every time two massive galaxies merge, their central black holes are brought together. The merger process is not instantaneous. After the galaxies collide and their stars intermingle, the two black holes orbit each other, gradually losing energy through a process called dynamical friction. They interact gravitationally with surrounding stars, transferring orbital energy to those stars, which causes the black holes to spiral closer together. Eventually, when they're close enough, they enter a regime where gravitational wave emission becomes the dominant source of energy loss. They spiral inward rapidly and merge in a burst of gravitational radiation so powerful that, for a brief moment, the merging black holes radiate more energy than all the stars in the observable universe combined. For a brightest cluster galaxy like the one hosting Phoenix A, mergers have been a central part of its history. These galaxies grow specifically by consuming smaller galaxies. Over billions of years, the central galaxy in the Phoenix cluster absorbed dozens, possibly hundreds, of smaller systems. Each of those smaller galaxies had its own central black hole. Some were small, millions of solar masses. Others may have been substantial, billions of solar masses, particularly if the merging galaxy was itself the central galaxy of a smaller cluster that was absorbed into the growing Phoenix cluster. Each merger added mass to the central black hole, not through accretion, but through direct combination. The relative importance of mergers versus accretion in building the most massive black holes is an active area of research. Models suggest that for black holes in the billions to tens of billions of solar masses range, both processes contribute significantly. Accretion dominates the total mass budget in some scenarios. Mergers dominate in others. The answer likely varies from one black hole to another, depending on the specific history of the host galaxy and the environment it inhabits. For Phoenix A, the environment strongly favors both channels operating at high intensity. The cooling flow in the Phoenix cluster delivers gas at extraordinary rates, fueling sustained accretion over long periods. and the cluster environment, dense with galaxies falling inward and merging with the central galaxy, ensures a steady supply of black hole mergers contributing additional mass. Phoenix A likely grew through a combination of prolonged, high-rate accretion fueled by the cooling flow and repeated mergers with the black holes of absorbed galaxies. But now, we need to confront the feedback problem directly. Because in most galaxy clusters, accretion and mergers do not produce black holes anywhere near 100 billion solar masses. The reason is feedback. And understanding why feedback failed to prevent Phoenix A's growth is perhaps the most important piece of the puzzle. As we discussed earlier, when a black hole accretes gas, it doesn't just swallow quietly. It produces energy. Enormous amounts of energy. Some of that energy escapes as radiation. Some of it is channeled into relativistic jets that drill outward from the black hole's poles. These jets carry kinetic energy and magnetic energy far out into the surrounding gas. In a galaxy cluster, the jets plow into the intracluster medium and inflate enormous cavities, bubbles of low-density, high-energy plasma that can stretch across hundreds of thousands of light years. The energy deposited by these jets heats the surrounding gas. This is the feedback cycle we described earlier. The thermostat that regulates cooling in virtually every cool core cluster we've studied. It's one of the most robust and well-observed phenomena in cluster astrophysics. X-ray images of galaxy clusters routinely show cavities inflated by jets from the central black hole. The energy contained in those cavities, estimated from their size and the pressure of the surrounding gas, roughly matches the energy the gas is losing through X-ray radiation. The thermostat works. Heating approximately balances cooling. The black hole grows modestly. The cooling flow is partially suppressed, and the system persists in a quasi-steady state. In the Phoenix cluster, the thermostat is struggling. Phoenix A does produce jets. It does inflate cavities. Observations confirm this clearly. The mechanical energy output of the jets is substantial, comparable to the jet power in many other massive clusters. But the cooling luminosity of the Phoenix cluster's core, the rate at which the gas is radiating away energy in X-rays, is so enormous that the jets can't keep up. The cooling is winning. The gas is losing energy faster than the jets can replace it. The result is that gas continues to cool in large quantities, continues to flow inward, continues to fuel both extreme star formation and continued accretion onto Phoenix A. Why is the cooling so powerful in this particular cluster? Several factors appear to contribute. The Phoenix cluster is exceptionally massive, which means its intracluster medium is exceptionally dense and hot. Denser gas radiates more efficiently. The X-ray luminosity of a plasma scales with the square of the gas density, so even modest increases in central gas density can produce dramatic increases in cooling rate. The Phoenix cluster's central gas density is among the highest measured in any cluster, which drives a cooling rate that overwhelms the jet heating. The geometry may also play a role. Jets deposit their energy in specific directions along the jet axis. If the cooling flow is coming in from all directions, but the jets only heat gas along two narrow channels, there may be significant regions of gas that never receive direct jet heating. The gas in those regions cools unimpeded, flowing inward to feed the black hole and fuel star formation. In clusters where the jets are more isotropic in their heating, or where the jets have had time to inflate large cavities that effectively heat gas in all directions, the feedback is more efficient. In the Phoenix cluster, the geometry may be less favorable for the jets. allowing the cooling flow to overwhelm the heating in certain regions. There's also the question of timing. Feedback is not instantaneous. When the black hole launches jets, those jets take time to propagate outward, inflate cavities, and transfer their energy to the surrounding gas. There's a delay between the moment the black hole feeds and the moment the resulting energy reaches the cooling gas far from the center. If the cooling time of the gas is shorter than this delay, the gas can cool and flow inward before the feedback has a chance to heat it. The Phoenix cluster's core has one of the shortest central cooling times ever measured in any cluster. The gas at the center is cooling so rapidly that the feedback loop may simply be too slow to keep up. By the time the jets respond to a surge in accretion, the cooled gas has already fallen inward, and the next batch of gas is already cooling. This creates a situation where Phoenix A can sustain high accretion rates for extended periods. Not permanently, perhaps. The system may oscillate, with periods of intense accretion alternating with periods where the jets temporarily gain the upper hand and slow the inflow. But even during the relatively quieter phases, the accretion rate may remain substantially higher than in most other clusters, simply because the baseline cooling rate is so extreme. Over billions of years, this sustained high-rate accretion, supplemented by black hole mergers from absorbed galaxies, built Phoenix A to its current extraordinary mass. The key insight is that Phoenix A didn't grow by violating any physical law. It didn't find a way around the Eddington limit or discover some exotic new feeding mechanism. It grew because it lived in an environment where the gas supply was so abundant, so persistent, and so relentlessly directed toward the center that even with feedback pushing back, the net inflow remained enormous. Think of it as a river and a dam. In most galaxy clusters, the central black hole builds a dam, its jets and radiation, that holds back the river of cooling gas. The dam isn't perfect. Some water leaks through, but the dam is strong enough to reduce the flow to a manageable trickle, and the black hole grows slowly. In the Phoenix cluster, the river is so massive, so powerful, so swollen with water that the dam, even though it's there, even though it's substantial, can't hold it back. Water pours over the top, seeps through the cracks, and floods the valley below. The black hole keeps building the dam higher, launching more powerful jets as it accretes more, but the river just keeps rising. The supply overwhelms the defense. This is not a permanent state. Eventually, one of several things will happen. The black hole will grow massive enough that its feedback becomes powerful enough to finally shut down the cooling flow. Or the gas supply in the cluster's core will be depleted by star formation and accretion, reducing the cooling rate. Or the cluster will undergo a major merger with another cluster, disrupting the cool core and temporarily shutting off the cooling flow entirely. Cool cores are fragile. A sufficiently violent cluster merger can mix the cool gas with the hotter gas farther out, raising the central temperature and destroying the cooling flow for hundreds of millions of years or longer. When the gas eventually resettles and cooling resumes, the system may reach a different equilibrium, potentially one where feedback is more effective. But for now, as we observe it, the Phoenix cluster appears to be in a state where the cooling flow has the upper hand, and Phoenix A has been the beneficiary. There is one more factor worth considering: the efficiency of accretion. Not all the matter that approaches a black hole necessarily falls in. The Eddington limit assumes a certain radiative efficiency. which is the fraction of the infalling matter's rest mass energy that gets converted to radiation before the matter crosses the event horizon. For a standard thin accretion disk around a non-spinning black hole, this efficiency is about 5 to 6%. For a rapidly spinning black hole, it can be as high as 30 to 40%, because the innermost stable orbit is closer to the event horizon, allowing the gas to release more gravitational energy before it falls in. Higher efficiency means more radiation per unit of infalling mass, which means a lower Eddington accretion rate in terms of actual mass consumed. A more efficient accretion disk produces more radiation pressure per kilogram of infalling gas, which makes it harder to push more gas in. Counterintuitively, a spinning black hole with a highly efficient accretion disk actually grows more slowly in mass than a non-spinning black hole accreting at the same Eddington luminosity, because more of the infalling energy is radiated away rather than swallowed. But in regimes where accretion is very high, particularly in geometrically thick flows where radiation can be trapped and advected inward, the effective efficiency drops. More of the energy gets carried across the event horizon with the gas rather than being radiated outward. This means the black hole gains mass more quickly per unit of luminosity. The gas falls in, carrying its energy with it, and the radiation that would normally push back never escapes. The black hole grows faster. This kind of advection-dominated accretion may have been important for Phoenix A, particularly during periods of peak feeding when the cooling flow was delivering gas at the highest rates. If the inflow was dense and fast enough to trap radiation within it, Phoenix A could have accreted more efficiently in terms of mass gain than a simple Eddington calculation would suggest. Each episode of intense accretion would add more mass than a standard model predicts, compounding the growth over billions of years. Putting all of this together, the picture that emerges is a black hole that grew through multiple reinforcing mechanisms operating simultaneously in the most extreme environment available. A massive seed, possibly formed through direct collapse or rapid early merging, gave Phoenix A head start. Sustained accretion fueled by the Phoenix cluster's extraordinary cooling flow provided a continuous, high-rate supply of gas over billions of years. Periods of super Eddington or advection-dominated accretion during peak feeding episodes may have accelerated the growth beyond what standard Eddington-limited models predict. Repeated mergers with the black holes of galaxies absorbed by the central brightest cluster galaxy added mass in discrete jumps, supplementing the continuous growth from accretion. And the feedback mechanism, while present and active, was unable to fully counteract the cooling flow, allowing the net inflow of gas to remain far higher than in most other clusters. No single one of these factors alone explains Phoenix A. A massive seed without sustained accretion wouldn't get you there. Sustained accretion without the extreme cooling flow of the Phoenix cluster wouldn't provide enough fuel. Mergers alone without accretion wouldn't add up fast enough. And none of it matters if feedback shuts off the gas supply, as it does in the vast majority of clusters. Phoenix A reached its extreme mass because all of these factors aligned simultaneously in one specific location for a significant fraction of cosmic history. This is what makes Phoenix A not just big, but genuinely informative for astrophysics. It tells us what happens at the extreme end of the parameter space. It shows us what's possible when every condition that favors black hole growth is pushed to its maximum. And it tests our theories, because any model of supermassive black hole growth that can't produce an object like Phoenix A under these conditions is incomplete. The existence of Phoenix A constrains our understanding of accretion, feedback, mergers, and the coevolution of black holes and their host galaxies in ways that less extreme objects cannot. Phoenix A grew for billions of years, fed by the most intense cooling flow known, supplemented by the mergers of countless absorbed galaxies, restrained but never stopped by its own feedback. The result is a black hole pressing against the upper boundary of what the universe can produce, not a violation of the rules, a demonstration of what happens when the rules are pushed to their limits. Phoenix A doesn't just sit at the center of the Phoenix cluster accumulating mass in silence. It acts. It shapes its surroundings on scales that stretch across hundreds of thousands of light years. It drives processes that influence how the entire central region of the cluster evolves. And the evidence of its activity is written in the X-ray light that streams from the cluster's core, in the cavities carved into the surrounding gas, and in the extraordinary blaze of new stars being born in the galaxy around it. This is what earns Phoenix A the title of cosmic monster. Not just how much it weighs, but what it does with that weight, the consequences it inflicts on the universe around it. Let's start with the jets, because every actively accreting supermassive black hole with sufficient mass and magnetic field structure can produce them, and Phoenix A is no exception. When matter spirals into the accretion disk around Phoenix A, a fraction of the energy released in that process gets channeled along the magnetic field lines, threading the disk and the spinning black hole itself. This energy launches two narrow beams of relativistic plasma, jets aimed outward along the rotational axis of the black hole, traveling at significant fractions of the speed of light. These jets don't just vanish into the void. They slam in the intra-cluster medium, the ocean of superheated gas filling the Phoenix cluster. And when a relativistic jet hits dense, hot plasma, it doesn't stop immediately. It drills forward, pushing the gas aside, inflating a cavity, a vast bubble of low-density, high-energy plasma surrounded by the denser intracluster medium. These cavities are enormous. In many galaxy clusters, the cavities inflated by the central black hole's jets span tens of thousands of light years across. In some cases, they reach hundreds of thousands of light years, far larger than entire galaxies. The Phoenix cluster's central region shows clear evidence of cavities in X-ray observations. The Chandra X-ray Observatory, which has studied this cluster in considerable detail, reveals depressions in the X-ray emission surrounding the central galaxy, regions where the hot gas has been pushed aside by the energy of Phoenix A's jets. These aren't subtle features. They represent genuine voids in the intracluster medium, regions where the gas density drops and the X-ray brightness fades, flanking the central galaxy on opposite sides, aligned with the expected direction of the jet axis. The energy contained in these cavities is staggering. Astrophysicists estimate cavity energy by measuring the cavity volume and the pressure of the surrounding gas. The work required to push that gas aside and inflate the cavity gives a lower bound on the energy the jets deposited. In the Phoenix cluster, the estimated jet power is enormous, on the order of 10 to the 46 ergs per second. That is comparable to the jet power in some of the most energetically active galaxy clusters known. Phoenix A is not quietly feeding. It is roaring, pumping energy into the intracluster medium at rates that rival the most powerful engines in the observed universe. And yet, As we discussed, it's not enough. The cooling luminosity of the Phoenix cluster's core exceeds what the jets can fully compensate. The gas keeps radiating, keeps cooling, keeps flowing inward. The jets push back, but the river of cooling gas overwhelms the dam. This imbalance is what makes the Phoenix cluster so scientifically important. It's a system where we can watch the feedback struggle in real time, not a system in equilibrium where heating and cooling neatly balance and everything looks stable, but a system in tension where two competing processes are both operating at extreme intensity and one is currently winning. The most visible consequence of the cooling flow's dominance is the star formation. We touched on this earlier, but it deserves a more careful look now, because the star formation in the Phoenix cluster's central galaxy is not just impressive. It's among the most extreme examples ever observed in any brightest cluster galaxy, and it connects directly to the same gas supply that feeds Phoenix A. The star formation rate in the central galaxy has been measured across multiple wavelengths. Ultraviolet observations detect the light of young, hot, massive stars that have recently formed. Infrared observations detect the thermal emission from dust heated by those same young stars. When you combine these measurements and account for dust absorption, the total star formation rate comes to roughly 500 to 800 solar masses per year. Some analyses have pushed the estimate toward 1,000, though the higher values carry more uncertainty. That means every year, gas equivalent to the mass of 500 suns is collapsing into dense clouds and igniting nuclear fusion. Every single day, more than one new solar mass of stars is born in this galaxy. In under 10,000 years at this rate, the central galaxy would produce enough new stars to equal the entire mass of Sagittarius A star, the black hole that anchors a galaxy of hundreds of billions of stars. The rate is relentless. It's industrial. It transforms vast quantities of raw gas into luminous stellar matter on timescales that are almost startlingly fast by cosmic standards. This star formation is happening because the cooling flow delivers enormous quantities of gas to the central galaxy. As the intracluster medium radiates X-rays and cools, gas condenses and flows inward. When it reaches the central galaxy and cools further, it forms the molecular clouds from which stars are born. The Phoenix cluster's cooling flow is one of the most powerful ever observed, and the result is one of the most powerful star-forming engines ever observed. The connection is direct. Cut off the cooling flow, and the star formation would plummet within a few 100 million years as the existing gas reservoir was consumed without replenishment. But here's what's remarkable about the interplay between the star formation and the black hole. Both are fed by the same source. Both are competing for the same pool of inflowing gas. Every solar mass of gas that collapses to form a star is a solar mass that doesn't reach Phoenix A. And every solar mass that falls into the black hole is a solar mass that doesn't form a star. The two processes are in competition, and the balance between them determines both the star formation rate and the black hole's accretion rate. In the Phoenix cluster, the total inflow appears to be large enough to sustain both processes simultaneously at extraordinary levels. The cooling flow delivers so much gas that even after hundreds of solar masses per year go into star formation, there's still a significant residual flow reaching the black hole. Phoenix A isn't starving despite the intense star formation. The supply is simply that abundant. This dual output, extreme star formation and extreme black hole accretion, happening simultaneously in the same galaxy, is rare. In most galaxy clusters, Feedback from the central black hole has suppressed the cooling flow to the point where star formation in the central galaxy is minimal. The brightest cluster galaxies in most cool core clusters form perhaps a few solar masses of new stars per year, or even less. They're quiescent, they're red and quiet. The Phoenix cluster's central galaxy stands out dramatically because both its star formation and its black hole activity are operating at levels that are almost unmatched elsewhere. Now we need to talk about something crucial. How do we actually know Phoenix A's mass? We've been using a figure of approximately 100 billion solar masses throughout this journey, and I've been careful to note that this is an estimate with significant uncertainty. But what does that actually mean? How do astronomers arrive at such a number for an object nearly 6 billion light years away? An object that emits no light of its own, an object whose influence can only be measured indirectly. Measuring the mass of a supermassive black hole is one of the most challenging tasks in observational astrophysics. For nearby black holes, the most reliable method is direct dynamical measurement. You observe the motions of stars or gas very close to the black hole, within the region where the black hole's gravity dominates over the gravity of the surrounding galaxy. By measuring how fast those stars or gas clouds move and how close they are to the center, you can calculate the enclosed mass using basic gravitational physics. This is how the mass of Sagittarius A star was determined. Astronomers tracked individual stars orbiting the black hole over decades, mapped their orbits with extraordinary precision, and derived the mass directly from the orbital dynamics. The result, about 4 million solar masses, is one of the most precisely known black hole masses in astronomy. For M87's black hole, the Event Horizon Telescope collaboration used a different approach. They directly imaged the shadow of the black hole, the dark silhouette created by the event horizon, against the glowing accretion flow. The size of that shadow, combined with the known distance to M87, gave a direct measurement of the event horizon diameter, which translates directly into mass. The result, about 6.5 billion solar masses, is among the most dramatically confirmed black hole masses ever measured. Phoenix A is too far away for either of these methods. At nearly 6 billion light years, individual stars near the black hole can't be resolved. The event horizon, while physically enormous, subtends an angle on the sky that is far too small for any existing telescope to resolve. We can't see the shadow, we can't track individual stellar orbits. We have to rely on indirect methods. The primary method used to estimate Phoenix A's mass relies on scaling relations. These are empirical correlations between a supermassive black hole's mass and certain properties of its host galaxy. The most famous of these is the M-sigma relation, which correlates a black hole's mass with the velocity dispersion of stars in the galaxy's central bulge. Velocity dispersion is a measure of how fast stars are moving in random directions within the galaxy. In a more massive galaxy with a deeper gravitational potential, stars move faster, and it turns out that the mass of the central black hole correlates tightly with this velocity dispersion. Bigger bulge, faster stars, bigger black hole. The correlation holds across a wide range of galaxy sizes and black hole masses. Another important scaling relation links black hole mass to the total luminosity or stellar mass of the galaxy's bulge. More luminous bulges, containing more stellar mass, tend to harbor more massive black holes. A third relates black hole mass to the luminosity of the galaxy's core region specifically. These scaling relations are calibrated using nearby galaxies where black hole masses can be measured directly through dynamical methods. You measure the black hole mass directly in dozens of nearby galaxies. You measure the velocity dispersion or bulge luminosity of those same galaxies, and you fit a mathematical relationship between them. Then you apply that relationship to more distant galaxies where direct measurement isn't possible. You measure the velocity dispersion or bulge luminosity of the distant galaxy, and use the scaling relation to infer the black hole mass. For Phoenix A, astronomers measured properties of the host galaxy, the brightest cluster galaxy at the center of the Phoenix cluster, and applied these scaling relations. The result pointed to a black hole mass in the neighborhood of 100 billion solar masses. This is an extraordinary number, and it sits at the very extreme end of the calibration range. The scaling relations were derived from galaxies with black holes in the millions to low billions of solar masses. Extrapolating them to 100 billion solar masses means extending the relation far beyond the range where it's been directly tested. This is where the honest uncertainty becomes important. Scaling relations have scatter, even among the nearby galaxies where both the black hole mass and the galaxy properties are well measured. The correlation isn't perfect. There's a spread. A galaxy with a given velocity dispersion might host a black hole that's 2 or 3 times heavier or lighter than the relation predicts. For well-measured nearby galaxies, this scatter introduces perhaps a factor of 2 or 3 uncertainty in the inferred black hole mass. At the extreme end, where Phoenix A sits, the scatter could be larger, because we simply don't have many directly measured black holes at these masses to anchor the relation. Additionally, brightest cluster galaxies are unusual objects. They form and grow through processes, specifically the cannibalization of many smaller galaxies, that are different from the processes that shape most galaxies in the calibration sample. It's possible that the scaling relations behave differently for these extreme objects. Maybe the black hole grew faster than the galaxy's velocity dispersion would suggest. Maybe it grew slower. We don't have enough data at the extreme end to know for certain. What we can say with reasonable confidence is that Phoenix A is extraordinarily massive. The data consistently point to a mass in the range of many tens of billions of solar masses. Whether the true value is 70 billion, 100 billion, or somewhere in between, the qualitative picture doesn't change. This is one of the most massive black holes ever identified. But the specific number, the precise value, should be understood as an estimate, not a definitive measurement. Future observations, particularly with next-generation telescopes capable of resolving the stellar dynamics closer to the center of the host galaxy, may refine this estimate substantially. The number might go up. It might come down. What it won't do is drop to a level where Phoenix A becomes ordinary. The environment, the galaxy, the cluster, all of them point to a black hole that belongs in the extreme upper tier, regardless of where the final mass measurement lands. This uncertainty is not a weakness of the science. It's an honest acknowledgement of how difficult it is to measure something nearly 6 billion light years away using indirect methods calibrated on much closer, less extreme systems. Science progresses by making the best measurements possible with available tools and being transparent about the limitations. Phoenix A's estimated mass is the best current assessment based on the available data. It will be refined. That's how science works. With that context firmly in place, Let's step back and ask what Phoenix A, at whatever its precise mass turns out to be, tells us about the universe. Because the value of this object extends far beyond its own event horizon. Phoenix A is a test case, a natural experiment conducted by the universe over billions of years, demonstrating what happens when every condition favoring black hole growth is maximized simultaneously. Theoretical models of supermassive black hole growth predict that there should be an upper limit to how massive these objects can become within the age of the universe. The constraints are real. The Eddington limit restricts accretion rates. Feedback from the black hole's own energy output, heat surrounding gas, and throttles the fuel supply. The finite age of the universe limits how many doubling times are available. The supply of gas in any given environment, no matter how extreme, is ultimately finite. All of these factors conspire to impose a ceiling, somewhere in the vicinity of 100 billion solar masses, give or take, depending on the model. Phoenix A appears to sit at or near that ceiling. It didn't overshoot it. It didn't find a way around the physics. It reached the ceiling by exploiting every available advantage. The most massive cluster, the most intense cooling flow, the most active galactic merging history, the most sustained period of high-rate accretion that the environment could support, and it arrived at a mass that is consistent with what the theoretical models predict as the maximum achievable under the most favorable conditions. This is scientifically satisfying in a way that might not be immediately obvious. When observations match theoretical predictions at the extreme end, it gives us confidence that the underlying physics is correct. The models say the maximum should be around this range. Phoenix A is around this range. That agreement suggests that our understanding of accretion, feedback, and black hole growth, while incomplete in many details, is capturing the essential physics correctly. We're not missing some major mechanism that would allow black holes to grow far beyond what we predict. The ceiling appears to be real, and Phoenix A appears to be pressing against it. But it also raises new questions. If Phoenix A is near the maximum, are there any black holes that exceed it? Could there be objects hidden in the distant universe, in clusters we haven't yet studied in detail, that push even further? The answer is probably not by much. The physics constraining growth doesn't change just because we haven't looked everywhere yet. The limits that cap Phoenix A's mass apply everywhere. There may be other black holes of comparable mass sitting in other extreme clusters at other cosmic epochs, but dramatically exceeding 100 billion solar masses appears to be genuinely difficult within the age of the universe, regardless of environment. There's also the question of what Phoenix A will become. It's still accreting. The cooling flow is still delivering gas. Stars are still forming. The jets are still firing. The system is still evolving. If the current conditions persist, Phoenix A will continue to grow, adding mass over the next few 100 million years. But the conditions won't persist forever. Eventually the feedback will gain the upper hand, or the gas supply will diminish, or a major cluster merger will disrupt the cool core. Phoenix A's growth will slow and eventually stop. It will settle into quiescence, a colossal relic sitting at the center of an enormous galaxy at the heart of a massive cluster, accreting at a trickle, no longer growing in any meaningful sense. It will endure essentially forever, on timescales far longer than the remaining lifetime of the stars around it. Black holes don't decay on any timescale relevant to astrophysics. Hawking radiation, The quantum process by which black holes slowly evaporate operates so slowly for a black hole of this mass that Phoenix A would need a time span vastly exceeding the current age of the universe, a number so large it makes the age of the cosmos look like a rounding error, to lose any significant fraction of its mass. For all practical purposes, Phoenix A is permanent. Long after the last star in the Phoenix cluster has burned out, long after the galaxies have faded into darkness, the black hole will remain. A gravitational monument to the extraordinary processes that built it. There is something profound about contemplating an object like this, not just its size, though the size is staggering, not just its mass, though the mass defies easy comprehension, but its existence as a product of cosmic history. Phoenix A is not an anomaly or a freak accident. It is the logical outcome of billions of years of physical processes operating exactly as the laws of nature dictate. Gravity pulls gas inward. Radiation carries energy away. Cooled gas condenses and falls. Stars form. Black holes feed. Jets push back. And in one extraordinary location, the balance tipped just far enough, for just long enough, that the result was an object on the very boundary of what the universe can produce. Every piece of this story connects. The mass of the cluster determines the temperature and density of the intracluster medium. The density of the gas determines the cooling rate. The cooling rate determines the inflow. The inflow feeds both star formation and the black hole. The black hole fights back with jets and radiation. But the inflow overwhelms the feedback because the cluster is so massive and the gas so dense, and so the black hole keeps growing, and the stars keep forming, and the cycle continues, each component driven by the same fundamental physics, each component influencing all the others in a web of interactions spanning millions of light years and billions of years. Phoenix A is not just a number on a page. It's not just a mass estimate with error bars. It's the endpoint of one of the most dramatic physical processes the universe has ever conducted. A process that started with the gravitational collapse of matter in the early cosmos, continued through the assembly of one of the most massive galaxy clusters in existence, and culminated in a single object so massive that its event horizon could swallow our entire solar system many times over. An object that warps space-time so severely that light needs weeks to cross it. An object containing the mass equivalent of a significant fraction of all the stars in the Milky Way. And it sits there, nearly 6 billion light years away, in the constellation Phoenix, at the center of its namesake cluster. We've never seen it directly. We never will. With current technology, we know it's there because of its gravitational influence on the stars around it, because of the scaling relations that connect its mass to the properties of its host galaxy, because of the jets and cavities it carves in the X-ray bright gas, because of the extraordinary star formation its feeding drives. We infer its existence and its mass from the evidence it leaves on its surroundings. Like an enormous animal that has passed through a landscape, leaving footprints and broken branches and trampled ground, Phoenix A reveals itself through the marks it makes on the universe around it. When you look up at the night sky, you won't see the Phoenix cluster. It's in the southern constellation Phoenix, and even from the best observing sites in the southern hemisphere, it's far too faint and too distant for the naked eye. You'd need a powerful telescope just to see the galaxies, and an X-ray observatory in orbit to see the gas. The black hole itself is invisible by definition. Nothing that crosses the event horizon ever returns. But it's there. nearly 6 billion light years away, embedded in one of the most massive structures the universe has ever assembled, fed by one of the most powerful cooling flows ever observed, surrounded by one of the most intense starbursts ever seen in a brightest cluster galaxy, pushing against the upper boundary of what physical law permits. An object that started as a seed, perhaps no more than a few 100,000 solar masses, billions of years ago, and grew through sustained accretion and relentless mergers into something that contains the mass of roughly 100 billion suns. We open this journey by comparing Phoenix A to Sagittarius A star, the 4 million solar mass black hole at the center of our own galaxy, 25,000 times more massive, an event horizon stretching 2,000 astronomical units, swallowing our entire solar system with vast room to spare, light needing more than 3 weeks to cross it, Voyager needing more than 5 centuries to escape it. We built up to the Phoenix cluster, one of the most extraordinary galaxy clusters in the known universe, with its superheated ocean of plasma, its staggering cooling flow, and its central galaxy blazing with new stars. We trace the growth mechanisms, accretion and mergers, operating against the constraints of the Eddington limit and feedback, pushed to their extremes by the most favorable environment imaginable. And we've confronted the uncertainty honestly. The mass is an estimate, and the specific number may shift as observations improve. But the qualitative reality is solid. Phoenix A is among the most massive black holes ever discovered, an object at or near the limit of what the universe can build. What makes it a monster is not just the mass, it's the totality of what it represents. The scale, the environment, the growth history, the ongoing activity, the jets carving cavities across hundreds of thousands of light years, the star formation blazing at hundreds of times the Milky Way's rate, the cooling flow that won't be stopped, the feedback that can't quite keep up. All of it, together, operating in concert, producing an object that tests our theories and rewards our curiosity. The universe, for all its vastness and apparent emptiness, occasionally builds something truly extraordinary. Not through exotic physics or impossible mechanisms, but through the patient, relentless application of the same laws that govern everything from the fall of an apple to the orbit of a planet. Gravity, radiation, thermodynamics, and time. Given enough of each, in the right combination, the universe can build something like Phoenix A, a single black hole pressing against the ceiling of possibility, shaped by billions of years of cosmic history, sitting at the center of one of the most extreme environments in the observable universe. A genuine cosmic monster, not because it defies the rules, but because it demonstrates just how far the rules can go. Thank you for staying with me through this journey. If this exploration gave you a new appreciation for the scale of the universe and the extraordinary objects hiding within it, a like or subscribe would mean a great deal. It helps more than you might realize. Sleep well tonight, knowing that somewhere out there, nearly 6 billion light years away, an object containing the mass of 100 billion stars sits quietly at the center of a blazing cluster, warping space-time across thousands of astronomical units, slowly swallowing the gas that flows toward it from an ocean of plasma larger than any galaxy. It has been doing this for billions of years. It will continue long after every star you've ever seen has gone dark. The universe built a monster, and now you understand why.